Alright, so 3.1 talked about finding vertex maximum and minimums. And I encourage you guys to read that section in your book so you can practice the word problems associated with that. Because finding the max and minimum of a quadratic equation is very important in word problems. But now we move on to 3.2. And in particular, I want to discuss properties. So 3.2 is going to be properties of polynomials. Properties of polynomials. And the key thing I want you to think about properties of polynomials is that we're talking about generic polynomials. They could range from f of x equals x squared, like a quadratic. They could be f of x equals x cubed. They could be f of x equals x to the fifth plus x cubed plus x squared. It could be different sort of bases or number of terms within your polynomial function. So what we need to know, they can range from all short shapes. And if you recall from 2.6, I believe, on transformation, I showed you several parent graphs, and I labeled the family of polynomials as the power functions. So that's technically, or that's what a polynomial function is. It's part of that power family. It's just your polynomial functions will have transformations with them. So they can have all sorts of behavior. If I were to give you, a simple grid, they can range from a quadratic that looks like this. They can range from that. Or we might even have a crazier behavior like this. This is x cubed. Or the parent graph is x cubed. And we might even have something along the lines of this, as you saw with your test. You might have a polynomial that has these crazy behavior where there's so many crazy peaks and local max and mins, or so many stretches that happens in between each interval, or something along those lines. We need to discuss properties of them. And in particular, the first property we're going to discuss that we need to make sure we understand is we need to discuss the terminology of smooth and continuous, especially if you're going into calculus. So we're going to say that polynomial functions, remember this, polynomial functions are smooth and continuous. I'm going to actually write continuous out. Now, you don't really understand what the word smooth and continuous means for polynomial functions until you reach calculus, maybe in Calc 2, Calc 1, but we are going to understand them intuitively. I am not going to give you guys a formal definition of what it means to be smooth and continuous. That's a bit too much. But the general idea of what it means to be continuous, if I were to draw this coordinate plane, I don't know what my polynomial function might look like. It could have some weird behavior. Let's say, or it might have some weird behavior like this. The key thing is that no matter what kind of behavior it has, it's going to be continuous. It's going to be continuous. That means if I were to draw from left to right, I am not letting go of my pen, marker, or whatever. They don't have any breaks. So, what's an example of one that's not continuous? The polynomial function must be continuous and smooth. However, if I were to draw, let's say this right here. Oh, now it's loading. Oh, I lost it. Give me 1 second. Let me reopen that real quick. Now let me share screen again. And we are back. So, you might have a function like this. An open circle and a closed circle. Boom. This is not a polynomial. Namely, it is not continuous. If you notice, at this x value, let's call this x equals 2. At this x value, it makes this jump. It is not continuous. In calculus, you'll learn what type of continuity or discontinuity it is. But right now, we're just going to say it's not continuous, so it's not a polynomial function. What's another property that I stated? Well, we talked about continuous. Now we got to talk about smoothness. Smoothness is very important. So, a function is smooth. This is continuous and smooth. Right here. This is continuous and smooth. So why is it smooth? Well, when we say the word smooth, we say that each part of our function doesn't have a cusp or a corner. So what does that mean? Let's take this function right here. Boom. This right here is what we call a corner. And it makes a corner because, hey, at that very specific value, we're not gradually, changing our y value or anything. No, it immediately jumps. It is not this smooth transition at all. It immediately goes from this crazy y value or this crazy slope and then instantly goes to this kind of slope. It has that crazy behavior. There's more formal definitions of defining what a corner is. I'm not going to go too much into detail with that because that takes a lot right now. But this is the intuitive idea of what a corner is. And this, because it has a corner, it cannot be a polynomial. You also cannot have a cusp. If I have a cusp, it is not a polynomial. So, not polynomial. If I were to instead have a cusp, it is still not a polynomial. So let's say instead of having this shape right here, I had this shape. We call these parts right here cusps. And you might notice a parent graph with the cusp, which is the absolute value of x. It has a cusp. Oops, I can't spell cusp right. So this is also not a polynomial because it has a cusp. Polynomial. And this is where you kind of get the idea of smoothness. The smoothness of how the graph transitioned from its local mins or local max. It's very smooth over here. It levels out. Over here, it's this instant change. Well, if you go to calculus, you learn about differentiability, and that's how they define cuspness, or if a function is cusped or not. So that is the idea of what a polynomial contains. Now we need to understand its behaviors. And first, let's talk about end behaviors. So we got to talk about the end behaviors, and then we got to talk about the behaviors that are not in the end. There's not really a good name for it, but I want to talk about the ends first because I think they're very important. So if we take a quadratic, let's take a polynomial. If I were to take a quadratic, you can have either this shape or this shape, where the end behavior is both going up, where the end behavior might be going up, and it might also be going up as x. So as a better way to say it, my end behavior as x approaches negative infinity, we can say the y also approaches infinity, or I'm not going to use the word or. That's for one side. If I look to the left, my y value goes all the way up. Similarly, if I go all the way to the right, as x approaches infinity, positive infinity, then the y will approach also infinity. So you notice they're both going up. Great. Well, with a polynomial, or a quadratic, it can also be reflected. So if I have a reflection, however, on the other hand, my quadratic might look like something like this. Boom. And in this case, we're going to say that as x approaches infinity or negative infinity, the y value approaches negative infinity. And then the other statement is as x goes to the right side, the y will also go negative. And this is very important. This is what happens in a quadratic. We can generalize this behavior with all of even power polynomials. If I have a fourth degree polynomial, it might behave something like this. Boom. If I have, if it's reflected across the x-axis, it might have this behavior as you saw on your test. It might also, if I have, let's say, a 6th degree polynomial, it might have something like this. Boom. Or all that stuff. So it's very important that we generalize this properly. So what we're going to say, even degree Remember what the word degree means. It's your highest exponent. I don't care about the other exponents. I care about the highest one. Your even degree polynomials. Here's how the end behaviors will play out. So I'm just going to give you a quick bulletin. You can read the book if you want formal definitions like I've shown earlier. I'm just going to give you the quick and easy way to think about them. If you have an even degree polynomial, the idea is that if a is bigger than 0, if your leading coefficient is positive, and we talked about knowing if we have a max or min, this is that same idea. If it's not being reflected across the x-axis, then we have the directions of your end behavior. For the left side, we have going up. For the right side, we also have going up. If a is negative, though, if our a value is, if our leading coefficient is negative, or if we have a reflection across the x-axis, then the left side is going to go up, the right side is going to go up as well. So the statement is, as x approaches infinity, then y would approach oh, I'm sorry. This should be reversed. I have to catch myself real quick. I apologize for that. The statement is, as x approaches negative infinity, then y will approach negative infinity. Or another one would be, as x approaches positive infinity, the y would approach negative infinity. That's what happens when you have a reflection across the x-axis, or if your leading coefficient is negative. They mean the same thing. All right, this is for even degree polynomials. We can generalize that, and I'll give you an image of that. So the image of this might be something like something like that. And then over here we might have, let's say, boom. The tail ends of them will go either positive infinity or both negative infinity. They both go in the same direction, though. That's the key thing with even degree polynomials. Well, odd degree polynomials now. Odd degree polynomials should be different from these guys. And we've seen examples of them and everything. We've seen x raised to the first power, which is a linear function. We've seen cubic functions, all of that. So we're going to say if your a value is positive, if there's no reflection at all, well, if you have no reflection, well, we have this weird behavior right here. Boom. Let's say this is a cubic function. It's a third power. That's an odd degree. Well, if you notice here, if we have no reflection at all, to the left side, we're actually going to go down, and to the right side, we're actually going to go up. So the end behavior, as x approaches negative infinity, y would approach negative infinity. As x approaches positive infinity, y approaches positive infinity. They alternate over here. The directions for your end behaviors alternate. The y value might go down and it might go up, depending on what x is approaching. If it's approaching negative infinity, it goes down. If it approaches positive infinity, your y value approaches positive infinity. So that's what an odd degree might look like. Now, I'm just generalizing. There's so many ways to draw a polynomial. I have to draw a generic version. So if we have a negative leading term, though, we're going to have it's still going to alternate, but it might have this behavior right here, and then our function I might give you as a representation might be along the lines of, let's see, I want to do that. Boom. Might be something like that. Boom. Remember, there's so many ways to do it, so many degrees. I'm just choosing something like the 5th degree or whatever, and it might have this kind of behavior. All I know is that at the very ends, one of them is going to go up, one of them is going to go down. If it's negative, the left side will go up, the right side will go down. And then if it's positive, all I know is that on the very left, it goes down. On the very right, it goes up. I don't know how much local mins or local maxes there are yet. We'll discuss that later on. But we're not supposed to know how much there are yet. But we can discuss the ends. We just can't discuss what's happening in between those ends right now. So that's the idea. You need to be able to use this information to sketch your graph. Today's topic is all about knowing how to sketch a graph, and I do require you guys to be able to sketch a graph, so that's very important. I expect you guys to be able to draw a graph given specific details, and this is going to help you out if you know the polynomial has an even degree or if you know it has an odd degree. All right, so that's great. We have that. We know polynomials are smooth, continuous. What happens if we have odd degree? What happens if we have even degree? Now, we need to talk about, hey, what happens in the middle? What happens in the middle? Well, this is where we're going to talk about some properties. In particular, if you remember, so this is going to be the middle of polynomial. I'm going to call this everything else in polynomials. Everything else. Oops, spelled else wrong. The main important part we need to talk about is zeros. Remember from last time, I stated that zeros is synonymous to the word roots, synonymous to the word x-intercepts, and solutions. Now, they all mean the same thing for our cases. In particular, when we graph them, we're going to be imagining the x-intercepts. And this is only if you have positive x, or not positive, you have real number x-intercepts. Later on, we're going to talk about complex, which you might have to change your definition of x-intercepts. But everything else in polynomials, we're going to talk about zeros, roots, x-intercepts, solutions. So the key important thing is these are equivalent. These are equivalent. These are equivalent. These are all equivalent. What I'm about to list down. Equivalent. If you have one, you have all of them. So the first statement I'm going to make is, so first we have to say let's let P be a polynomial. P of x be a polynomial function. So remember what the definition of a polynomial function is. It just has some degree of your x terms. And C is an element of real numbers. Let's let C be a real number. I don't know what real number. It could be 4, it could be 5, it could be 3.2, it could be square root of 3, it could be any of that stuff, all right? What are logically equivalent, we're going to have these statements that are logically equivalent. The first one is, we can say that if C is a 0 of P. So, if one of these are true, all of them are true. So C is a 0 of your polynomial. Well, if that is true, we can also say C is an x-intercept of P. Or I should say the graph of P. Graph of P. So if we have a 0, that is also your x-intercept, which we have synonymous terms for the word 0. So that's also saying if we have a solution, if we have a root, if we have any of those stuff. Well, now we have another one that's logic or that's equivalent to all of these. So if we do have this x-intercept, if we have an x-intercept, we can say that x minus c is a factor of P of x. That's very powerful. If we have an x-intercept or if we have a 0, we can say that x minus c is a factor of P of x. That's very important. What else can we say? Well, if we have any of these, we can also say that x equals c is a solution of P of x equals 0. This means if I set my polynomial function equal to 0, then c is a solution. X equals c is a solution. These are all logically equivalent. So let's take an example. What I mean. One of these, if one of these are true, all of them are true. I'm not saying they're true until one of them is true. So let's take an example. Example, P of x equals x. Let's take a generic polynomial expression. Well, if I factor this out, I could say P of x equals x minus 2 times x plus 3. I encourage you guys to practice that. You guys should be able to factor nicely. Well, now, if I set P of x equal to 0, so if I set this equal to 0, I get x minus 2, x plus 3, and then I get x is equal to 2 comma negative 3. What does this mean? That means, this means x equals 2, negative 3 is a solution to p of x equals 0. If I set my output equal to 0, these are my solutions. What else does it mean? It also means that, well, the solution is x equals 2 and negative 3, but that means that x minus 2, and so I have to do x minus whatever my solution is, and x minus negative 3, which is equal to x plus 3, is a factor of p of x. That's a very powerful thing. The moment I have a solution, I know what the factors are. The moment I have a factor, I know what the solutions are. So I can go backwards as well. That's a very strong statement. And I recommend you understand what this means. And if you look into your review, it actually plays a role in the last question. I gave you guys an example of what happens if I plug something in and I get 0 out. Well, that automatically should tell you it's a factor. What does this also mean? Well, this also means that x equals 2 and x equals negative 3 is the x-intercepts of p of x. And the last thing is that these, so we can say 2 and negative 3 are zeros of p. Why do they call them 0? Because if I plug them in, I get 0. That's the idea. That's why we call them zeros. But these 4 statements, just because I solved this out right here, this p of x, and I had my factors and found a solution, I can say all 4 statements. They come with each other. The moment I have one, I have all of them. Instantly, I know that, hey, if x equals 2 and x equals negative 3, those are my x-intercepts. My factors are going to be x minus 2 and x plus 3, which are right here. They are right there. Boom. I also know that these numbers are my zeros and all that good stuff. So these are very important. So those are some important properties that we have figured out. Now we cover a name theorem, and this name theorem is very, very powerful in mathematics. You might think it's obvious, but in mathematics it is not clear because a lot of things that we have to consider. So this is called the intermediate value theorem. Some of you guys might see it as IVT or whatever. If you're going into calculus, they just try to use acronyms, but I guess I should write it out for you guys. Some of you guys aren't going into there. Intermediate value theorem. This is a very, very powerful rule. And it's clearly going to be a very important one because it has a name. The moment it has a name, it's very powerful. Mathematicians prove this. So the idea is that, hey, if I have some value right here of my function, and then some value here of my function, I have 2 points in my function. It's a polynomial function. I don't know how it would behave. It could behave any way. Let's call this P of A. Let's call this P of B. This is located at A. This is located at B. I don't know how this function behaves. It can behave like this. Boom. It can behave like that. It can also behave like this, a straight line. It can behave like this. It can behave all sorts of ways. But the key thing in the intermediate value theorem, it states that if I have one that has a negative output, this is a negative output because the y value is negative. If I have a positive output, or vice versa, if I have a positive output and a negative output, the idea is that somewhere, if P of A is less than 0 and P of B is bigger than 0, if one is positive, if one is negative and one is positive, then somewhere in my interval, let's say A comma B, somewhere in there, I don't know exactly where, somewhere in there, P of C equals 0. Somewhere in there, I'm going to touch this x-intercept at the value C. somewhere in there. And remember, P of something equals 0 means my output is 0, which means it's an x-intercept. This means C is x-intercept. This might not be obvious, but because our function is continuous and smooth, and I started at a negative portion to a positive portion, I have to touch the x-axis at some point. I don't know where it touches it. It can touch it all the way over here. It can touch it all the way over here. But it's going to touch the x-axis before I cover all the way to my point B. In this interval right here, this is an interval. This is not a coordinate. This is an interval. In this interval, I will be touching the C value. Well, the converse can be, or not the converse, but if that's true, well, I can also say the same for the alternate if P of A was positive and P of B was negative, right? If this one was on top instead, and this guy was on bottom instead, that still should hold true. So we can say that as well. So we can say if P of A is positive and P of B is negative, then there exists some C. I don't know where it's at. All I know is that it's in this interval. It could be anywhere in that interval, but P of C equals 0, which means that's an x-intercept. It's a 0. And this follows along with number 4 in our list right here. Where's number 4 at? If I number these. Yeah. So look, see? It says here, if x equals C is a solution of P of x equals 0, these are all logically equivalent. If you have an x-intercept, automatically we can say that, hey, if I plug that C into my function, it's going to give me 0. It's going to output 0. That's the idea. All right, so now we talked about the end behaviors, and we talked about when it has to cross the x-axis. Well, the last thing is that we got to discuss is factored form polynomial. So when we talked about quadratics, a specific polynomial, we had general form, we had vertex form, and now there's one last form that plays a role. Now with polynomials, we might not have a vertex form, but we do have a general form and factored form. What is this factored form? So this factored form, entire function, it's going to be fully factored. That's the first thing. It's going to be fully factored in this form. Moreover, you can find zeros easily. You can find the zeros or x-intercepts very easily in factored form. And the last one we're going to say is, let's see what I want to say. No, that should be enough. Everything else is very intuitive. So the entire function is fully factored, and find zeros are very easy. So we talked about what a polynomial is expressed as. It's a of sub n times x raised to the n power plus a sub n minus 1, x sub n. It's going to be a lot of terms. If there's n degrees, there's going to be n terms. Some of them might be equal to 0, but there's going to be n terms at the end of the day, or n plus 1, I apologize. But factored form is nicer than that. So if I have a polynomial p of x, what factored form is going to be in the form of, and I'm just going to use some value a, boom, a. It's going to be in the form of a times x minus c, let's call it c1, x minus c2, and then this is going to keep happening, dot, 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 all the way to x minus c of n. Boom. All the way to the nth degree. I can turn a polynomial fully factored out. And this is going to tell us your roots are at c1, comma c2, comma dot, 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 all the way to cn. These are where your roots, your x-intercepts are located at. Boom. So, an example of this. Example. Let's say I have a polynomial function. Let's say 3 times x minus 2, x minus 3, and then let's say x minus 4. Boom. This is in factored form. This is in factored form. So earlier, when I give you a polynomial right here, to find out the roots easily, you always put it in factored form. That makes it easier to find the roots. So I can generalize this with a higher degree polynomial, not just a quadratic. I can go to the third degree. I can go to the fourth degree. Well, in this case, we have it to the third degree. Why is it to the third degree? Well, each of these are raised to the first power. If I were to FOIL all of them out, you would see my highest exponent is x cubed. So I encourage you to try that out, expand it, and see if it goes to x cubed. But that's the idea, because when you're multiplying with this, when you're multiplying things, you add the exponents. So this is in factor form. These are all my roots. I can say that this is going to have a vertical stretch of 3. You might even have, a reflection. Who knows? You could have if it was negative. But this is the idea of your polynomial roots. Now, how do we graph this? How to graph? How do we graph this? This is very important. If I were to draw a coordinate plane of this, I have to consider a few things. First, and behaviors. So first of all, this is a third degree polynomial. I have 1, 2, 3. Now, if you expand it all the way, you should have x cubed plus something. I don't know, 3x cubed plus all these other terms. I don't know what the other terms are. If you want to calculate, you can. But I know that I have a third degree polynomial. So this is third degree. And if you remember from our third degree, or what a third degree polynomial does, it's an odd degree, so it follows this property right here. If your if your leading coefficient is positive, we have this. If it's negative, we have this. Well, over here, our leading coefficient is this guy right here. This is clearly positive. And because it's positive, and it's an odd degree, I have my end behaviors as down, then upwards. Let me just make sure if it's right, but I should be correct there. Down, then upwards. Yep, if it's positive. So boom. So I have that. That means I don't know how my function behave, but all I know is that all the way to the left, it's going to go down. All the way to the right, let me use a different color marker. All the way to the left, it might go down, and all the way to the right, it's going to go up. I don't know what happens in between. I do not know at all. But all I know at the moment is that this behavior happens. Well, now we go into our roots. We have 3 roots. 2, so we have x equals 2, x equals 3, and x equals negative 4, or positive 4, I apologize. These are going to be our x-intercepts, roots, and our solution, all of that good stuff. So, at x equals 2, 1, 2, 3, 4, 1, 2, 3, 4, I know I'm going to touch the x-axis at these points. Boom. I know I'm going to touch it at these points. So it's a matter of now I have to connect them. But the problem is, how do I connect my graph? So there's a lot of alternatives you can have. Am I gonna connect them all like this? Like that? Am I gonna connect them like this? Like that? There's all sorts of ways you can connect these. All I know at the moment is that I am going to connect them. I just need to know how. Am I going to cross over? Am I going to bounce? Am I going to still bounce? Am I going to still bounce? Boom. How do we know how we're going to sketch the graph? We have the end behaviors, and we know in the middle it's supposed to touch the x-axis. These are the x-intercepts. Sometimes they might cross through the x-intercepts. Sometimes they might bounce off. How can I make that decision? I'm going to let you know in this case, we're actually going to have a function that does this. Boom, boom. It's going to cross. It's going to cross, and we're going to cross. How can I know it's going to cross the x-intercept at my, or how can I know it's going to cross the x-axis at my x-intercept? So I forgot to write this down. Plot x-intercepts. How do I know, though? It's this idea of multiplicity. multiplicity. What does multiplicity means? The multiplicity of a root x equals c. Multiplicity of a root at x equals c. Remember, the word root is also zeros. It's also x-intercept. It's all those terminology. The multiplicity of a root x equals c is the number of times x equals c repeats. It's a number it repeats. The number of times it repeats. So, what the heck does that mean? Well, this is how to give you the most basic idea. Let's say I draw a graph, quadratic. This is f of x equals x squared. If I were to solve for this, find out the x-intercept, it's located at 0. Right? Now, if I calculate algebraically, I substitute my function, I output for 0, x squared. And then I solve for it. Wait a minute. I have to square root both sides, if you remember. Then I have to do plus or minus. Correct? Well, then I get x is equal to plus or minus 0. Now, in this case, it's weird because some people argue that 0 is positive or negative. It's both, actually, in this case. But the idea is that I have two solutions. I should have two solutions. Whether my solutions are the same or different does not matter. I have two solutions. This is two solutions. Your solution is x equals negative 0 and x equals positive 0, which are still x equals 0 and x equals 0. Notice I didn't put parentheses around them. I don't want to count it as an ordered pair or an interval. I just want to list my solutions. So that means 0 repeats twice. Multiplicity is 2. So the 0 x equals 0 repeats twice, which means it has multiplicity of 2. Multiplicity of 2. It repeats twice. So in this case, it repeats twice. And there's some information you can get out of this that we'll talk about in a bit. Another example, we might have, let's say, p of x equals x minus 3, x plus 4 squared, x cubed. In this case, our roots are going to be x equals 3, x equals negative 4, x equals negative 4. This happens twice. And x equals 0, x equals 0, x equals 0. It happens 3 times. Now, when you list me the solutions, you don't have to write the same solution if it repeats, right? But instead, I encourage you guys to think about its multiplicity. So we say x equals negative 4 has multiplicity 2. X equals 0 has multiplicity 3. So instead of repeating these like I just did, I just replaced it by saying it has this number of multiplicity. If it repeats twice, it has multiplicity 2. If it repeats 3 times, we say it has multiplicity 3. And why does this repeat twice right here? Because this is the exact same thing as saying x minus 3, x plus 4 times x plus 4 times x times x times x. This happens 3 times. This happens twice. All right? And in this case, if you guys weren't aware, my degree, the degree of this guy, degree, is actually going to be 6. Because I have x cubed. This is raised to the second power. So it's like x squared. If I multiply, that's x to the 5th. And this is to the first power right here. So it's going to be x to the 6th power. That's going to be my highest degree, or my degree. So that's multiplicity. But how does multiplicity, how does it help for graphing? How does it help for graphing? Well, we have to consider the multiplicity of every single time we cross the graph. So I'm going to say if multiplicity is odd, function or graph crosses the x-axis. So I'm saying if it's odd, graph crosses x-axis at x-intercept. So you got to look at your x-intercept. If your x-intercept has multiplicity that's a number odd, then your graph will cross that x-axis. If we look over here, boom, this number right here, x equals 2, multiplicity 1. That's an odd number. So when I drew my graph here, when I drew it over here, notice that I immediately crossed my x-intercept. I immediately cross it. Same with here. All of these are multiplicity 1, which is an odd degree or odd number. So every single time I touch my x-intercepts, I will cross that x-axis like I am. Boom. And then, oops. You could go back to it. Well, I'm not sure if I can go back to it or not. I'm just going to draw this. But it's going to cross it every single time. That's how I know it's going to be in this behavior. Well, over here, the multiplicity of f of x equals x squared, that's an even number. The multiplicity of 0 is 2 in this case. It's 2. It repeats twice, which means that I don't cross my x-axis. So when I was drawing this out, notice that I touched the x-intercept, but I immediately bounce upwards. So we're going to state that. If the multiplicity is odd, graph crosses the x-axis at the x-intercept. An example like that, you might have something along the lines of, let's say your x-intercept is over here. You can have something like this. You can also have something like, that's if it's 1, if it's a higher degree. If you increase if your degree is odd, if your multiplicity is odd, but then you still have an odd degree, if you have an odd multiplicity, all it means if it's higher is that it's going to oscillate more. So let's suppose on that same point, on that exact same point, I decide to draw, this has multiplicity 1, multiplicity x equals 2. Let's say it is at x equals 2, and let's say it is at x equals 2. Let's say it has multiplicity 3. If it has multiplicity 3, it should still cross. But the problem is that it's going to oscillate instead now. So when it goes over here, it might oscillate like this. Boom. It might oscillate a bit. It's not going to directly cross through like your multiplicity of 1. It's going to oscillate just slightly. And then when you get higher multiplicity that are odd, it's going to oscillate even more. So it's very hard to draw this without knowing the multiplicity. Now, if it's even, if x equals c is an x-intercept with even multiplicity, oops, if it has an even multiplicity, then at x equals c, graph will bounce at x-axis. It will bounce at x-axis, or I'm not going to say x-axis, I'm going to say x-intercept. It will bounce at x-intercept. So, the example you saw earlier was a quadratic, so let me give you another example. Let's say I have two examples. The most common one is the quadratic. If you notice this bounce right here. This is at x equals, let's say 5, multiplicity 2. It will bounce. You're going to draw your line, your graph. As I'm drawing my graph here, boom. As I'm drawing my graph, my function, I'm across the x-axis, but because it has an even multiplicity, I can't cross through the x-axis. No, instead, I bounce. Now, you still have to draw it smooth. This doesn't look smooth, but it is. So remember, your function still be smooth. It should not have a cusp. Boom. That same example, let's say at x equals 5, let's say now we have a multiplicity 4. It's still even multiplicity, but what's going to happen is it's going to oscillate more. So when I do my oscillation, it might have this behavior right here. Boom, boom, boom. I don't know. I might start up here. I don't know how my graph will look like. It can look something like this. This is very hard to draw. Let's do blue. So I might have it like this. It needs to be wider, I guess. Might be something like that. It oscillates more in where that is happening, but it still does not cross it. Actually, to make it even more obvious to see, it might be more clear if I draw this. Something along those lines. No, I like the other one better. It's just very hard to draw in general. But the idea is that it will oscillate much more. Boom. Than just a regular quadratic. It's very hard to draw that snake-like behavior like how I did over here. I have to show you that it crosses through, but it's not. It might not be a straight line that crosses through that x-intercept, but it kind of waves inside. And that's supposed to be happening here as well. Okay? If you want a better image, you can look into your book for that. So, with that idea, we need to be able to sketch a graph. So, let's see if we can sketch a graph. Sketch. Let's take the polynomial p of x. I'm going to put in factored form so it's easier to deal with. But let's say I have it in factored form as x plus 2 cubed x squared times x plus 1. And I'm going to put, I could put a negative here. All right. All the negative means is that's going to reflect across the x-axis. So first, you need to figure out the degree. All right. This has a 3. This has a 2. This is technically raised to the first power. So 3 times, or 3 plus 2 plus 1. Because they're all multiplying, so you add the exponents. Right. Then we're going to have degree is 6. Degree is 6. It's an even degree. So if I draw my x and y axis, if I draw my x-axis, I have an even degree. Now I have a reflection. Reflect across x. I don't know the shifts. I'm not going to deal with the shifts. I just know it reflects across the x-axis. Let me change it. Orange is not the best color for this, at least. Boom. So if I have an even degree and it's being reflected across the x-axis, that means the value here, the a value, is less than 0, so it's negative. That means I have the end behavior going like, if even, if it's, them going in the same exact direction. I don't know how my function behaves at the moment, but I know at the very ends, it's going to go down and it's going to go up. I don't know how it might go down. I don't know how it might go, but all I know is that it's going to be all the way down and all the way up. Okay? Now, we got to look at our x-intercept. We have x equals negative 2, x equals 0, and x equals negative 1. This has multiplicity of 3. This has multiplicity of 2. And this has multiplicity of 1. All right? That's how much time it repeats. Well, now I got to plot my x-intercepts. X equals 2. Let's say this is x equals 2. Somewhere around here, x equals 0 is right here. And x equals negative 1 is right here. So these are my x-intercepts. Now I just need to know how to connect them. Well, I know that this part right here has to touch the x-intercept. It has to touch that right there. Now it's just more of, do I cross or do I bounce? Well, it has multiplicity 3, which means that I'm supposed to actually kind of oscillate a bit, but it will cross through it. If I oscillate slightly right here, it will cross through. Like that. It will cross through because it's an odd multiplicity. Now, I have to eventually go down to, I guess I go to negative 1 now, so I'm looking at this one now because negative 2, then negative 1, then 0, so I apologize. But now, this has multiplicity 1. So that means I have to cross through on this one right here. It has to cross through straight up. It does not oscillate as much. It just straightly cross throughs. And then the last one. Oops. I drew my end behaviors wrong. It should have been both down. I apologize for that. And then I cross through, or the last one right here, it says when I touch the x-intercept 0, I have to bounce. I don't cross the x-axis. Instead, when I touch that x-intercept, I immediately come back to the other side. I do not cross it at all. So this is a general idea of my function, how it behaves. Now, you might draw a better function. You might have drawn it like this. If you had drawn it like this is probably a more accurate illustration. I just want to give you the ideas of how it plays around the x-intercepts and the end behaviors. This is how we're going to sketch our graph. Now, notice, I did not talk about the local max, the local minimums. I did not talk about the stretches. I did talk about reflections, but I didn't talk about the stretches. I didn't talk about shifts. For sketching a polynomial, that's a lot of things to consider. We'll only consider local maxes and local minimums tomorrow. But that's the idea. And I'll leave it at that. I will catch you guys later. Take care. Bye.